Dalton's atomic theory. So when we talk about Dalton, got to remember that Dalton was a scientist in the early 1800s, and he thought of atoms. The word atoms comes from atmos, which means small indivisible sphere. So what we thought of as was an atom was this small sphere that could not be divided. It was the smallest particle of matter. So elements were made of these tiny particles that could not be divided into anything smaller. Each element was characterized by the mass of its atom. He said that atoms have the same element have identical masses, and that atoms of different elements have different masses. He said that atoms will combine in small whole number ratios to form new substances we call compounds. Well, we just talked about that. A chemical reaction does not create or destroy atoms, but it rearranges them. So this is the conservation of matter that we've talked about. So this is what Dalton thought. So we go through this. What was an atom made of? What is an atom made of? Well, Dalton didn't know. They didn't have the technology that we have now. The atom was the basic unit of an element. It still is the basic atom. The atom still is the basic unit that can enter into a chemical reaction. And nearly 100 years later, another scientist, J.J. Thomson, discovered the electron. This, 100 years later, was when we found out that part of Dalton's theory was wrong, that atoms are not tiny, indivisible spheres, but yet they are these little parts that have other smaller parts. They're made out of smaller particles that we're going to talk about. So by the mid 1800s, it actually became evident that atoms are divisible, and there's an internal structure to the atom known as subatomic, sub within the atom, so within the atom, subatomic particles. So that means Dalton was wrong, but some of what he talked about is still true. So J.J. Thomson used what's called a cathode ray tube. And many of you are probably looking at this going, what is this thing? Well, my generation actually, and most of you probably actually had them in your houses. If you had a television, so this is TV, this is the front that you watch, and it had a big old back on it. This big old back is called a CRT. So you may have had a computer monitor that was a CRT monitor, or a CRT television that is a cathode ray tube. And they don't want you to just toss those around or whatever. You have to get rid of them specially. So cathode ray tube has this stream of particles that comes through here. So there's a stream of particles that comes right through here, and it's going to be moving faster because of the plates that we're going to charge it through. We've got the cathode, the negative end, and the anode, the positive end, and we're going to put these particles through here. Now there's charged plates. This is the negatively charged plate and a positively charged plate, and this stream of particles is going to be split, where the positive particles are going to be attracted to the negative plate and get deflected upward, and the negative particles are going to be attracted to the positive, so opposites attract. They're going to attract to the opposite and get deflected the opposite way. So we have different types of radiation that we're going to talk about what they used to determine this. But what J.J. Thomson was able to discover using this, so what he did was he varied the voltage across these plates right here. He varied how it did, and then he measured how much this beam of particles bent. So he measured how much it would bend, and then he was able to, from that data, get the charge to mass. So this is the charge to mass ratio of an electron. So this is what he did. He had this beam of particles, and he was able to use a magnet to deflect it. So this magnet is repelling, so whatever they have the same charge. And then he was able to attract it. And by measuring how much this bent, he's able to get that charge to mass ratio. I'm going to post this link. So I want you to watch this on Blackboard, okay? It's just going to help you get another view of what happened. R.A. Millikan did what we know as the oil drop experiment. So he devised an experiment to find the actual charge of an electron. So if we have the charge to mass ratio from J.J. Thomson, and we get the charge of an electron, we can use these two numbers together to find the mass mathematically. So they're going to kind of work together and put their information, they're going to collaborate and get their information to get the mass. So he took and he had this fine mist of particles up here. I mean, a fine mist of particles that are smaller than anything that we could ever detect. And he had a positively charged plate and a negatively charged plate. And in this plate, there's a tiny pinhole right there. So this tiny pinhole where these little particles can come through one at a time. Then he varied the voltage across these two plates. He changed it so that one drop would just be suspended between the two plates. And he was able to take a look by using the telescopic eyepiece. So he's able to see what's happening. So this is what's happening here. We got this one particle that's going to be just floating there in between these two plates. And by doing that and looking at what the voltage was on those plates at that time, that would give him the charge of the electron, because the exact opposite positive charge would attract it enough so it wouldn't go anywhere, but it wouldn't continue to fall. So that charged droplet, he found the charge. So this is the charge here, divided by the charge to mass ratio, and they're able to then find the mass of an electron. So now we know we have this particle, this tiny particle that is smaller than an atom. Because back when Dalton was looking at things, the smallest thing that you could use, the smallest particle, the smallest bit of matter that you could use to go into a reaction was a hydrogen atom. But now we have something that is much, much smaller. So where are they getting these beam of particles? This is an important thing to remember, because a lot of these scientists, you know, they're dealing with radioactivity and not necessarily in a very safe manner. So a radioactive substance, and we're going to deal with these more at the end of this chapter and in chapter 22, are substances that are going to spontaneously emit these particles. So you have a substance that's radioactive. We see it here inside this block. So this radioactive substance is here inside the block, and it is spontaneously emitting particles. Now it does that, it can be very harmful depending on what type of particles. So we put it into a lead block. Just like when you go to get x-rays, you wear a lead apron so you don't get exposed. So you're going to go, it's going through the charged plates, and then it's going to get separated. Alpha rays are positively charged, so they're going to go towards the negatively charged plate because opposites attract. Beta rays are negatively charged, so they're going to go towards the positively charged side because they are opposite to attract. And gamma rays are not charged, so they're going to go straight ahead. So that's when we talk about them using a beam of particles, that's what we're talking about. So the next thing is Thomson thought that the atom was this blob that had positively charged particles and negatively charged particles just throughout it like this, and that was it. But then somebody else came along and did this pretty simple experiment called the gold foil experiment, where they sent this beam of particles at this piece of gold foil. And if this atom was like Thomson had said it was, the particles should go straight through. So this is what they expect, and that's what we see here. This is what we expect, that the particles should go straight through. But about 1 in 8,000 of those particles bounced straight back. And that took a long time to explain. I mean, a year or so of thinking about what do these results mean? This is not what we thought was going to happen. What does this mean? So when they bounced straight back, it must mean that they hit something dense in the middle. And that, folks, is how we discovered the nucleus. So the gold foil experiment, this is Rutherford, by the way, his name was Rutherford. So Rutherford said that, let me go back a minute. So this is Rutherford's gold foil experiment, and he discovered the nucleus because these particles bounced straight back at him. They must hit something dense in the center of the atom. So Rutherford's model said that hydrogen has a mass of 1, which it does. Then helium should have a mass of 2. But if you all look at your periodic table, you're going to notice that helium has a mass of 4. So what else is going on there? So James Chadwick and Rutherford actually worked together. They're colleagues. Not always, scientists don't always work very, good together, but they discovered what's called the neutron. So the neutron is the third subatomic particle, and it's got no charge. It's neutral. So we have positively charged protons, negatively charged neutrons, and now we have, excuse me, I just said that wrong. Positively charged protons, negatively charged electrons, and neutral neutrons. So we have neutral, no charge. So there was a third particle kind of hidden in there that we didn't realize because it wasn't charged. I do want you to watch this video as well. I will post it on Blackboard for you. So protons, neutrons, and electrons. So this is our new model of the atom. This is the nucleus right here in the center. You can't even really tell I'm coloring over that. And this area is mostly empty space that is thinly populated with electrons. So this is the nucleus. It contains almost all of the mass of the atom. It contains the protons and the neutrons. And this area here is thinly populated with electrons. It's called the electron cloud. So protons are positive, electrons are negative, and neutrons are neutral. Neutrons are very slightly larger than protons. We can see that here. Neutrons, protons, almost exactly the same until we get to the thousandths place. But for all intents and purposes, they're the same size and mass for what we deal with. And the electron, if you look here, is much, much smaller. So times 10 to the negative 28th versus times 10 to the negative 24th. So for all intents and purposes, for what we calculate at this level, we're going to consider the mass of an electron essentially negligible. So when we add up the mass of an atom, we're only going to need to add the mass of protons and neutrons. If we want to know the charge, we need to look at, so for this is mass, we add those two, but for charge, we look at these two because neutrons are neutral. So discovering these subatomic particles definitely said that Dalton's theory was incorrect. Atoms are divisible, so now we know we have a subatomic structure, but another part of Dalton's theory is also incorrect. All atoms of an element are not identical. We have what are called isotopes, so they have different masses. So then we're going to talk about what are called isotopes in just a moment. So the newest and most up-to-date model of the atom we use is called the nuclear model of the atom. So we went through, this is called the plum pudding model. That was the one with J.J. Thomson. The plum pudding model, and most of you have never even eaten plum pudding, so I call it the chocolate chip cookie model just to give you a view, where the doughy part is the positive one and the chocolate chips would be the negatively charged electrons. That one is not correct. Then they came up with this one, which we still see today, where we have this orbital type thing drawn. This is called the planetary model of the atom. And that's not correct. And we haven't quite talked about that one yet because there's a scientist named Heisenberg that says we can't know exactly where the electron is and the speed that it's going at. So that is why the planetary model doesn't work. So the nuclear model of the atom looks at this in a quantum mechanic, basically a quantum mechanical model of the atom. And we have that small, dense nucleus and this cloud of electrons, which is thinly populated with electrons. And the number of electrons exactly equals the number of protons in a neutral atom. So every atom contains a small, dense nucleus. All positive charge and nearly all the mass of an atom is in the nucleus. The nucleus is surrounded by mostly empty space. An atom is mostly empty space, and that space outside the nucleus is thinly populated by electrons. So if this atom is neutral, the number of electrons and the number of protons must be equal because there's no charge. Now we're going to talk about isotopes. But these symbols are important, especially if you plan on taking any of the standardized tests in the future. They like to look at these symbols and throw them around at you and see if you know what they mean. So you're going to want to take a look at those. So the atomic number Z is the number of protons in an atom. So let's look at number 2. Helium has 2 protons. Right? So whatever the number of the atom is, that's how many protons it is, and that will never change. So the atomic number always equals the number of protons. Always, no exceptions. In a neutral atom, it's also equal to the number of electrons, but it has to be a neutral atom. So the number of electrons can change, but we start out neutral and then we form ions from there. The mass number, this one never fails to confuse people. The mass number is not found on the periodic table. The number you see on the periodic table is called average atomic mass. So the mass on the periodic table is called the average atomic mass. And that averages all of the elements, all of the naturally occurring, all of the how should I say this? All of the naturally occurring non-radioactive species in their natural abundances is how it does that. And we will take a look at that as well and learn how to calculate that, so don't worry. But the mass number is not found on the periodic table, so how do we find it is really quite simple. It's really simple to find, and we always give you the right information. So make sure you practice this because, again, for some reason it's always confusing. The mass number, A, which is down here, is the sum of the number of protons plus the number of neutrons. So Z plus N, the number of neutrons, gives you A, the mass number. The mass number is specific to an isotope. So the definition of an isotope is atoms that have the same number of protons or the same atomic number, but a different mass number, A, because they have a different number of neutrons. So the atomic number Z is down here. This is called a nuclide symbol. You will see it as X, A, Z. Sometimes you'll see it as X or A without Z. Why don't we have to put Z there? Well, we don't need Z because we've given you X, and you can look at your periodic table and find it because the atomic number will always be on the periodic table available for you. So this is actually just a review slide. Again, I find this to be confusing for people, and especially in class, we'll go over and over and over it. But the atomic number Z is equal to the number of protons. It can be used to identify elements. It can be equal to the number of electrons in an atom only if it's neutral. The periodic table is arranged according to increasing Z, and each element has a different Z. Mass number A is the number of protons plus the number of neutrons, and it's not found on the periodic table. Okay, so I want you to pause this, and I want you to tell me the atomic number of the next couple. What is the atomic number of iron? What is the atomic number of silver? What is the atomic number for zinc? And how many protons does chlorine have? Pause it. The atomic number of iron is 26. The atomic number of silver is 47. And the atomic number of zinc is 30. How many protons does chlorine have? 17. Does everybody understand that these are all the same question? Essentially, I'm asking you, what is the atomic number? So isotopes, they're represented by this nuclide symbol. So what do the nuclide symbols tell you? This is a nuclide symbol for nitrogen 14. So this is how we name an isotope. So this is how to write the name of an isotope. If you have the actual isotopic mass for something, because none of them are a whole number, we round to the closest whole number for the mass number, and you write the name of the element, a dash, and then A. So this has a mass number of 14, it's nitrogen 14. This has a mass of 15, it's nitrogen 15. Okay, so I'm going to erase that now. So what does this tell me? If this is A and this is Z, it tells me it's nitrogen. It tells me it has 7 protons that come from Z, 7 electrons. How do I know there are 7 electrons? How do I know that the electrons equal the protons? Because if I look at this, there is no charge written here. So if a nuclide symbol were charged, this is where the charge would be. It would be, +2. Actually, not +2, it'd be 2+. I actually get kind of 2+, or, 3-. Whatever that number is, that would be the charge. Since there is nothing written there, it's no charge, so it's neutral. So these would be the same. And then there are 7 neutrons. How do I know that? Because A minus Z, or 14 minus 7, is 7. In nitrogen 15, I have 7 protons and 7 electrons, but I have 8 neutrons because 15 minus 7 is 8. This has already been written here the whole time, so this would be the nuclide symbol for oxygen 16. O for oxygen, 16 for the mass, and 8 for this. So let's try a different one. Since that one, the animation didn't work, tell me for chlorine 37. I forgot my dash. So it's chlorine 37. Let's pause it and write the nuclide symbol. So this would be the nuclide symbol for chlorine 37. I don't know whether it exists or not. Sometimes I just make things up. So if you check it and it doesn't exist, it doesn't have to be real for me to ask you for this. Honestly, I do try to make things as close to reality as possible, but sometimes when I make stuff up, I make stuff up. All right, so let's practice. Pause this, try it, then we're going through the answer. So pause it. It's on you. If you don't pause it, you're not getting the practice. An atom has an A equal to 12 and a Z equal to 6. How many neutrons does it have? Has 6, because 12 minus 6 is 6. An atom has a Z equal to 12 and 14 neutrons. How many protons? What is the mass number and what is the element? It has 12 protons. The mass number is 26 and the element is magnesium because we're looking for number 12 on the periodic table. So isotopes, most elements have 2 or more isotopes, but so they're again elements that have the same atomic number but different mass numbers. These are the 3 for hydrogen. Now remember, when we name our isotopes, we take the element name, a dash, and then the mass number. The ones for hydrogen actually have special names just because it's hydrogen and they're used a lot. So this is hydrogen 1. I want you to think about how many protons, neutrons, and electrons each one of these have. So this is hydrogen 1. It's also called protium. How many protons does protium have? So protium has 1 proton because it has a Z equal to 1. And it has 0 neutrons. And because there's no charge, it would also have 1 electron. Hydrogen 2, or deuterium, is going to have how many protons? 1, because it has a Z of 1. How many neutrons? Well, 2 minus 1 is 1, so it has 1 neutron. And this is hydrogen 3, which is called tritium. And how many protons does it have? 1. How many neutrons does it have? 3 minus 1 is 2. So it has 2 neutrons. So isotopes generally exhibit the same chemical behavior for all of these chemical properties, so we can use these in certain ways. Deuterium is one that we use a lot in like NMR, so that proton NMR, I should say. So we're not actually seeing these protons within the NMR. They don't act the same in the NMR, so we can take those out so we don't get our solvent mixed in with our compound that we're trying to figure out the structure of. Atomic mass units are an important unit that we made up. I mean, a dozen means 12, right? But it didn't always mean 12 till somebody made up a unit and said a dozen is 12 of any object. So AMU, or atomic mass units, allows us to relate a unit to mass so that we can weigh large numbers of atoms by count large numbers of atoms by weighing them. So if I go to order screws to build a house, I'm going to build a house or build a deck or something, I don't buy screws. I'll have 12 screws, please, or 12,000 screws, please, right? I order them by the pound. So we count by weighing, and we do that in chemistry as well. So 1 atomic mass unit is equal to 1/12 the mass of carbon-12. So this is all going to be based off of carbon-12. It wasn't always, but it is today. The mass of 1 atom of carbon-12 is defined to be 12 AMU. 1 AMU is equal to 1.66 times 10 to the negative 24th grams. And if that number doesn't look familiar to you, you can go back. Oh, we have to go back a ways. Wonder if I can even hear. Hold on. Wrong button. Okay. I'll get it, guys. Just give me a second. If we go back to, and I don't think you can actually see what I'm doing right now, so I have no idea. If you can, cool. I'm not trying to hide anything from you. To this slide here, if you look at this number, 1.674927, that number is very close, 1.672 times 10 to the negative 24th. These are all the mass of an atom and a neutron. So these masses are always times 10 to the negative 24th, which, remember how easy it is to forget to write an exponent. So sometimes it's easy just you forget to write it, all of that. So 1.66 times 10 to the negative 24th, I would love it if you all took your calculator and said 1 divided by 1.66 times 10 to the negative 24th. Now, if you really did that, if you do that right now, you pull out your calculator and you do 1 divided by 1.66 times 10, you can use your E button, remember, to the negative 24th, you're going to get a number that says 6.02409638 times 10 to the 23rd. 6.02 times 10 to the 23rd is a number we're going to talk about later called Avogadro's number. And that number, being related to atomic mass units, also allows us to relate this to what's called the mole. If you remember, the mole is how much matter is in something. The mole is what we use for that. We talked about that in the units chapter. So when we talk about atomic mass or atomic weight, the average, I like to actually call this average atomic mass, but I made these slides off of your book, is actually the weighted average of the atomic masses that are naturally occurring isotopes. So the naturally occurring isotopes in their weighted average. So this is a weighted average. Now, many of you have forgotten how to do that. So we're going to take a look at how to take a weighted average. So that would be this number that we find on the periodic table. Remember, that is not, this is not the mass, it's not A. It's not the mass number that we were just talking about. How do we calculate average atomic mass? Well, we have to be given the mass of the isotopes, or we could, be given the average atomic mass and asked to find one of the isotopes. But either way, it's the sum. Remember, this symbol means the sum of the isotope mass times the fraction of the isotope. How do I get the fraction of the isotope? This is given to me in percent. Percent. How many cents are in a dollar? 100, right? Percent. So percent means out. It means out of 100. So anytime we have percent, it means out of 100. To get to a decimal, you divide by 100. So 98.93 divided by 100 gives you 0.9893. 1.07 divided by 100 is 0.0107. So we just divide them by 100. That's how you get those. All right, so we take the sum of those and we multiply by 100. So we say the isotopic mass, this would be the sum of 12.000000 times 0.9893, and this would be added to this number times 0.0107, like this. So 0.9893, and remember we're doing the sum of all of these. We could put brackets here if you wanted to. It's multiply these, and then add them together. Remember, multiplication comes before addition. When we do that, you get a big long number, but we can only keep the 12.0. If you compare that to the periodic table, which says 12.01, it's because they use something with more precise information than what we did. Because if you look at our information here, 1.07 is only 3 sig figs, so we can only have 3. But this actually comes down to being 12.01 if we look at it, because we actually have to look at the number of decimal places in the end. So that can be kind of tricky because you're going to be using the addition and subtraction rule and the multiplication and division rule. So look at both of those when you're doing your sig figs. All right, I want you to pause this and try it. So pause it and try it. I'm not walking you really through it right now. I'm just going to kind of go through the answer. So we're going to take this mass and multiply it by this decimal, so 0.6917, and this number times 0.3083, and we add them together. So that would look like this, and we would get 63.55. That's enough for now. We'll be back for more.